friends for talk today. My name is Kim. I'm supervised by Carl Guren, Graham Healy, and Manjit Chan. My talk today is titled Gaze Couple On-Screen Information Lifelogging. So I'll go through the content today by firstly introduce my work and related research, and then I'll go through my hypothesis and research questions. Next, I will summarize my progress and research plan, and finally, I will summarize the talk today. So for introduction and related work, as we might all observe, computer and internet are widely adopted, which enable us to access to almost everything. So the number of information we see in daily computer usage is huge, and very often we will find useful information that we want to keep so that we can look back in the futures. Like we take notes from an online course, and then we can use it to revise our knowledge. Or you might find an interesting tutorial video and you want to save it somewhere to watch it later. But clearly, it is impossible to manually keep every single information like that. And it raises the need of a system that helps you to keep all of those informations and allows you to search for the desired informations. So there are many research fields that focus on this, and personal information management PIM tools are one of them. So these PIM tools focus on indexing the files stored on a computer based on their metadata and contents. And these systems only focus on limited file types, which is not generalized well to all information displaying on screen. So on the other hand, we have Lifelogging, which is a way that you can passively record your life using multiple sensors. So we can have like images, heart rate, calories, steps, or GPS, and all of these forms a big personal multimodal archive. And given that big data set, searching for moments in the data becomes an attractive problem. And over the years, the Lifelogging community witnesses the introductions of many interactive retrieval systems with many variants in the way that we can search and interact with Lifelogging data, ranging from the web-based to application-based and virtual reality. So taking the Lifelogging concept to apply on information, clearly it is possible to do so by passively record the information display on screen along with the mouse and keyboard data. So on the left here, you can see the Loggerman, which is a software that designed to do so. And it was actually developed by a PhD student in DCU. On the right, you can see the Human Screenome project, which is initiated by Stanford just recently, focused on analyzing the mobile screenshot to understand the human well-being on social media. So none of these were focused on the retrieval aspect of the capture on-screen information, and indexing and retrieving the on-screen information is still an area of research. However, having only screen capture is not ideal. Like given this screen, you might read it differently than the way I do. So it would be useful if we can further understand that where our attention is shifted when we read on screen. And thanks to the development of eye tracking technology, the movement of the eyes can now be estimated and give us the exact location where we are looking at. And using this, we can understand human interests and use it to form a personalized retrieval system. So the main topic of this research is Infologging, which is a new form of Lifelogging that emphasizes on logging and retrieving the information we encounter on screen. And the retrieval process can be done by an interactive retrieval system. An example query that you can do on the Infologging is something like, for example, like the name of a famous restaurant that I have read on a news article about top places in Ireland, but I forgot the title of article or the link to that article, so I can search for it. So Infologging is the system that does the things. So eye tracking will be a new source of data that will be used in this research, and the research methodology uses the comparative analysis on reusable test collections. And since this research required the development of new data sets, so you will hear me mention a lot about NTCAR, which is a testbed and community for information access research. And every new data set I generated will be utilized to organize research tasks on NTCAR to benchmark my method against the other state-of-the-art approaches. So moving on to hypothesis and research questions. I define my hypothesis to be by capturing how people consume multimodal on-screen information. Through the analysis of hormone patterns, it is possible to derive the personal gatekeeper visual features for on-screen information that can be used to support the effective infologging retrieval. So based on that, 4 research questions have been formed. Like the research question 1 simply focus on the development of a novel infologging dataset. And given that multi-modal infologging dataset, I will first focus on the text retrieval and then move to the multi-modal retrieval problem. And these were the 2 sub-questions in research question 3. Moreover, in terms of text reading, we have different strategy to read the text, like skimming, scanning, reading. So that's why I have that in research question 2 to understand the reading strategy being used. And lastly, by referring to the state-of-the-art system in Lifelogging, I will come up with an interactive search engine for Infologging in research question 4. So more to the progress today. On the right is the Gantt chart of my progresses and plans. The progresses are highlighted in blue and the remaining tasks are highlighted in red. The future planning also includes the collection of 2 new datasets and 1 user study as pointed out. So for the first progress I have made, the interactive Lifelog search engine was the first step I took to understand Lifelogging and the state-of-the-art retrieval system. It is useful to begin with Lifelogging since there's already a benchmarking dataset out there which I can base on to develop a retrieval system. And this system will be the basis to create a retrieval system for Infologging later on. So the Lifelog search challenge is a research challenge that benchmarks the Lifelogging retrieval engines. And this is a real-time offline competitions in which a query is given, and then the team should find 1 image that matches the description as quickly as possible. And the score will be based on precision and search time. There's also a penalty for wrong submissions. So having participated in LOC twice, here's the version of interactive search engine for Lifelog that we call the LabSeeker. So here's the interface of the LabSeeker. And since LabSeeker is the concept-based retrieval, we incorporate a wide range of concept detectors such as object, scene attributes, scene text in order to describe the image in details. And we have the elastic sequencing, which is a way that we can adjust the time to verify the events faster. And it also groups the images of the same area into a big group to help to search faster. And based on the area grouping, a transitional graph can be formed to help filter the search results. So here's my result in participating in LSC. The figure B is a result in 2019, which LabSeeker achieved among top 4. And in figure C, which is the result in 2020, LabSeeker only came in mid-range. And this is unfortunately due to a bug that we introduced while deploying the system, and we forgot to turn off the debug mode. So looking closer to the result in 2020, LabSeeker actually worked very well on the descriptive topic, achieved among the top 5 in terms of score, but performed poorly on temporal query. And that's where we spot out the bug. And we will furthermore improve the LabSeeker in this year, LSC 2021 challenge, and the LabSeeker version 3 is coming soon. So that addressed the research question 4.1, which is the understanding the state-of-the-art interactive retrieval system in Lifelog. Moving to the microactivity detection in Lifelogging. Activity is a main part of retrieval system, and almost all LC queries are about recording specific activities. However, there are very broad classes like eating, cooking, and walking. But within that, there are many small activities like when you're walking, you might reading on screen, you might answering a phone call, or you might writing some notes. And all of these provide a deep level of details of what activity is being performed. And that is the reason why we introduced the task called microactivity retrieval task in NTCR 15, which incorporate new source of data to capture microactivity. such as the EOG to capture eye movements and the accelerometer to capture the hand movements and head movements. So the goal was to predict 20 classes of microactivities. So here are some of the microactivities that we are interested in, like drinking water, counting money, playing with a ball, doing housework. So we propose a total of 5 models, which 2 on the left are the baseline model and 3 on the right are more advanced model, which focus on deep learning and machine learning techniques. And the results suggest that the ITPS, which is the image tabular pairwise similarity models, achieve the best result. And this was due to it learns the similarity between 2 activity instances rather than classify a single activity instance as the other 4. And comparing to the other team that participate in the MAR task, our result is not far from the best team. So the construction of the MAR datasets was similar to Infologging, and that I will discuss later. But most of the software developed in MAR can be reused to collect the Infologging dataset. So that helps partially have to address the research question 1. For the on-screen text reading activity detections, which is part of the research question 2, studying the text reading initially on Infologging datasets is not ideal, since there are many control variables will influence the outcomes. So therefore, an external dataset will be constructed with the aim is to understand what information humans consume on screen and whether they comprehend them. So this use a dataset, the text from the race dataset, and focus on 4 different behavior like reading, scanning, skimming, and proofreading. To assess the comprehension, we use the multiple choice question, which is also part of the race dataset. And this dataset will be utilized to the NCCI 16 reading comprehension for information retrieval RCAR tasks. And the data collection process includes a person sitting in front of a screen with an eye tracker located at the bottom of the monitor. And the volunteer will be asked to read a given text under predefined behaviors. So here's the setup of the eye tracker. And on the right, you can see is what actually happened in the eye tracker. Your eyes and your pupil will be tracked. And due to the COVID outbreak, the collection of this dataset is on pause, but I was able to conduct a pilot experiment on 3 participants. And as you can see on the left, this is a visualization of a person skimming on the text, and every dot in here is defined to be a fixations, which is the moment where our eyes being still at for a period of time, and the connection between 2 dots is conjugates. So when we visualize the signal from eye tracking, we can see some of the patterns of different activities. In reading, the signal gradually increase and suddenly drop, and the similar pattern can be seen in skimming, which is the 3rd row, but the slope is steeper. In scanning, the signal fluctuates a lot, and in proofreading, there are more plateaus. So based on that insight, and with the reference to the related literature, I consider a list of 10 features from our movement data as shown on screen. And there are features that are time series data and scalar data. So for the time series data, I will further engineer them to convert them into feature vector using the bag of features, which has the statistical functions. And the second way is to use the histogram to capture the distribution of data values. And the feature vector from the time series data will be concatenated with the scalar features to form a single vector representations. So I use a list of most common machine learning models to perform the classification of reading activities. And as illustrated in the result, random forest got the highest accuracy score. And it also suggested that the bag of features capture the time series better than the histogram. And in terms of the activities, the confusion matrix on the right suggested that reading and scanning are highly distinctive, while the other two can be easily misclassified into reading and scanning. This is mostly due to the behavior of the participant when they perform the skimming and proofreading. If the person skims too slow, it becomes a reading activity. So with this result, it is worth to note that this is just a first phase of the experiment on a small scale data set. And once I have the full data set, I will further perform the feature selection to understand what features contribute to the classification of reading tasks. So that helps to address the research question too. For the research plan, so far I've gone through 3 main progresses and experiments. And now I'll briefly summarize my plan by listing out 7 tasks to be done in the future. For the first start is a collection of the Infologging dataset. I'll shortlisted a list of 7 activities from the daily computer uses to focus on. And these activities are selected based on the survey from 18 and 19. And there will be activities that are topic-driven and the others are free. The topic-driven will introduce the common topics among the participants, while the other allows unique topic to appear in a single participant. And there will be 20 participants in total in this study. And based on that, with the Infologging dataset, we'll further preprocess the data by grouping the similar screens and based on the screenshot and extract the text and images from the screen capture. And with that data, we're able to develop the baseline retrieval system to provide initial results to compare with the later approaches. And this can be easily done by employing the proven retrieval pipeline in LabSeeker. And that helps to address the research question 1. Going to research question 2, I had the reading activity classification pipeline earlier, so it's time to extend and improve it. So to improve the reading activity detection, I further employed the workbook features as introduced in 20, and I'll further perform the modern feature selection and I talked earlier. For the RCIR task, which is reading comprehension in information retrieval, I will further study whether the participant comprehend the text after reading. By inspecting the relationship between eye movement and text, and then examine more features on this relationship, such as the word omission rate, the number of refixation, and so on. And that helps to address the research question 2. So for research question 3, for the text content, since different persons read the text differently, so I focus on generating a personalized representation for the on-screen text. Based on the finding from Cage Rayner, interest of an area correlate with the gaze duration. So I will examine the fixation duration as an input for the term weighting functions to support the text retrieval. And for images, we can interpret them as regions of visual concept. So a similar approach in task 5 can be applied to generate a vector representation for image as well by considering each region as a term. So since both of text and images are now represented by terms, they can combine to form a single vector representation for retrieval. And that helps to address research question 3. So lastly, the interactive Infologging retrieval system will be developed by modifying the LabSeeker that we have for Lifelogging. And then the user study will be conducted to evaluate the interactive system with the automatic retrieval approaches in research question 3. And a follow-up survey will be established to seek for the improvement in user interface and user experience. And so here's the overview of the progresses and the plans for research questions in general. So to summarize my talk today, for the last 2 years, I completed the GTA training elements. I coordinated and participated in many research tasks and developed an interactive retrieval system, which is LabSeeker, to address the research question 4.1. I acquired the experience in designing and conducting experiments and data collection with volunteers to help address the research question 1, and built an analysis pipeline to address the research question too. So I published a total of 16 papers and resulting in the H index of 8 and I index of 8. To summarize the contribution of this research focus on infologging, which is a new form of live logging, which capture the on-screen information and use the eye tracking as a new data source to support the process of retrieval. And it's also construct a novel infologging dataset, explore the eye movement features for retrieval and representation methods. And it also provides an interactive search engine for infologging. So here's the list of paper published. So the first 5 of them, I was the first authors. For the paper plans, most of my work I would target at the multimedia conferences like MMM or ICMM or ICMR. But for the result in eye tracking initially, I would focus on ETRE, which is Symposium on Eye Tracking Research, which is part of the CAI conference. And for the retrieval, information retrieval results, I would target at the SIG-IR conference. And that's the end of my presentation, and thank you all for your attention.